Introduction to verification. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, focusing on networking. Also, hit the bell icon to get notified of new videos. Today we're going to learn how Merkle tree verification works, but we're keeping it simple. No complex math formulas or complicated terminology. Just a straightforward explanation of how you can prove a piece of data is authentic. Think of it like this. Imagine you have a huge library with millions of books. Someone claims they have a specific book from your library. How can they prove it without showing you all the books? That's what Merkle tree verification solves. We will walk through the process step by step, using simple examples and visual diagrams. By the end, you will understand exactly how verification works and why it is so powerful for blockchain and distributed systems. The basic idea. Let's start with the basic idea behind Merkle tree verification. It's actually quite simple when you break it down. Imagine you have 4 transactions you want to organize. You hash each one individually. This means you run each transaction through a function that creates a unique fingerprint for it. Then you pair them up and combine each pair, hashing them together. You keep doing this, pairing and hashing, until you end up with just one hash at the top. This top hash is called the root, and it represents all 4 transactions. The magic is this. If you want to prove one transaction is in this group, you don't need to show all 4 transactions. You only need to show a few hashes along the way. It's like showing a path from your transaction up to the root. This is incredibly efficient. For 1,000,000 transactions, you only need about 20 hashes to prove one transaction is authentic. That's the power of Merkle tree verification. A simple example. Let's work through a real example with 4 transactions. We'll call them transaction A, B, C, and D. This will make everything concrete and easy to follow. Step 1. Hash each transaction. Transaction A becomes hash A. Transaction B becomes hash B, and so on. These are our starting points at the bottom of the tree. Step 2. Combine pairs. We put hash A and hash B together and hash them, creating hash AB. We do the same with hash C and hash D to create hash CD. Step 3. Combine these two. We put hash AB and hash CD together and hash them one more time. This gives us the root hash, one single hash representing all 4 transactions. Now here's the cool part. This root hash is like a seal on the entire group. If anyone changes even one letter in transaction A, the root hash will be completely different. That's how we detect tampering. What is a proof? Now let's understand what a Merkle proof actually is. This is the key to efficient verification. Suppose you want to prove that you have transaction C from our 4 transaction example. You need to show me that transaction C, when properly combined with other hashes, produces the root hash I already trust. The proof consists of the transaction itself plus a few helper hashes. For transaction C, you need hash D, C's partner, and hash AB, the combined hash of A and B. That's it, just transaction C, hash D, and hash AB. With these 3 pieces of information, I can verify that transaction C is authentic by computing up to the root and checking if it matches. Notice we didn't need transaction A, B, or D. We didn't need most of the hashes. Just a small set of helper hashes that let us reconstruct the path to the root. This is why Merkle proofs are so efficient. Step 1. Hash the data. Let's walk through the verification process step by step. We'll verify transaction C from our example. The first step is simple. Hash the transaction you are trying to verify. We take transaction C and hash it to get hash C. This is our starting point. We now have the hash that represents our transaction at the leaf level of the tree. Think of this as finding your starting position. You begin at the bottom of the tree with your transaction's hash. From there, you need to climb up to the root, using the helper hashes provided in the proof. Step: combine with partner. Now we take our hash C and combine it with its partner. The proof told us that hash D is C's partner at the leaf level. We put hash C and hash D together and hash them. This gives us hash CD, the combined hash of C and D. We've now moved up one level in the tree. We started at the leaves with hash C, and now we're at the next level up with hash CD. Notice we needed hash ID from the proof to do this. That is why the proof includes helper hashes. They let us compute our way up the tree without having all the actual transactions. Step 3. Combine again. We're almost there. Now we take our hash CD and combine it with hash AB, which was also included in the proof. We put hash CD and hash AB together and hash them one more time. This gives us the final root hash. We've reached the top of the tree. We started with transaction C, combined it with helper hashes at each level, and computed our way all the way up to the root. Compare roots. This is the final and most important step. We compare the root hash that was just computed with the trusted root hash. If they match exactly, the verification succeeds. This proves that transaction C is authentic and really is part of the tree. If they don't match, the verification fails. Either transaction C is not the real transaction, or someone tampered with the proof. The beauty of this is that the comparison is binary. Either it matches, or it doesn't. There's no gray area. The hash function guarantees that if anything is wrong, the hashes won't match. Why this works? Let's understand why this verification process actually works and why it's secure. Hash functions have special properties. If you change even one tiny bit of the input, the output completely changes. This is called the avalanche effect. So if someone tries to give you a fake transaction C, when you hash it, you will get a different hash C. This different hash will combine with the proof hashes differently, and you will end up with a different root. The fake root won't match the trusted root, so you will know something is wrong. The verification fails and you reject the fake transaction. Similarly, if someone tampers with any of the proof hashes, the final root will be different. Any change anywhere in the chain is detected. Efficiency benefits. Now let's talk about why this is so much better than alternative approaches. Imagine if you had to show all 4 transactions to prove you have transaction C that's 4 times the data. For 1,000,000 transactions, you'd need to send 1,000,000 transactions just to prove you have one. With Merkle proofs, you only need a few hashes. For 4 transactions, you need 2 helper hashes. For 1,000,000 transactions, you need about 20 helper hashes. Each hash is small, just 32 bytes for the common SHA-256 algorithm. 20 hashes is only 640 bytes. Compare that to potentially gigabytes of transaction data. This efficiency is why Bitcoin wallets on phones can verify transactions without downloading the entire blockchain. They just download small proofs and verify them. Order matters. There is one important detail we need to understand. The order in which you combine hashes matters. When we combined hash C and hash D, we had to put them in the right order. Hash C on the left, hash D on the right, because that is their position in the tree. If we switched them around and put hash D on the left and hash C on the right, we would get a different combined hash. The verification would fail even though we have the right pieces. The proof needs to tell you not just which hashes to use, but also which side they go on, left or right. Most implementations achieve this by including position information within the proof. Bigger trees. Our example had 4 transactions, but real Merkle trees are much bigger. Let's see how verification scales to larger trees. With 8 transactions, you need 3 levels in the tree and 3 helper hashes in the proof. With 16 transactions, 4 levels and 4 helper hashes. Notice the pattern. Every time you double the number of transactions, you only need 1 more hash in the proof. This is what we call logarithmic scaling. For 1,000 transactions, you need 10 helper hashes. For 1,000,000 transactions, 20 helper hashes. For 1 billion transactions, 30 helper hashes. The proof stays small even as the tree grows huge. This is the fundamental efficiency that makes Merkle trees so powerful. Security guarantees. Let's talk about the security guarantees that Merkle tree verification provides. Hash functions are designed so that finding two different inputs that produce the same output is virtually impossible. This is called collision resistance. For SHA-256, which Bitcoin uses, you would need to try trillions upon trillions of combinations to find a collision. It would take all the computers on Earth millions of years. This means an attacker can't create a fake transaction that produces the right hashes. They can't forge a proof that passes verification. When verification succeeds, you can be virtually certain the data is authentic. The probability of a false positive is so tiny it's essentially zero. Real-world example. Let's see how this works in a real-world scenario. For example, a Bitcoin mobile wallet. Your phone doesn't have space to download the entire Bitcoin blockchain, which is hundreds of gigabytes. But you want to verify that someone sent you Bitcoin. Your wallet downloads just the block headers, which contain Merkle roots. Each header is only 80 bytes. For years of blockchain history, that's maybe 50 megabytes. When a transaction comes in claiming to be yours, your wallet asks a full node for a Merkle proof. The proof is just a few hundred bytes. Your wallet verifies the proof against the Merkle root in the header it already has. If verification succeeds, you know the transaction is real and confirmed in the blockchain. This is how millions of people use Bitcoin on mobile devices. Merkle tree verification makes it practical. What can go wrong? Let's understand what happens when verification fails and what that tells us. If someone gives you wrong transaction data, the hash you compute won't match the expected hash. Your computed root won't match the trusted root, and verification fails. If someone corrupts one of the helper hashes in the proof, the combinations will be wrong. Again, your computed root won't match, and verification fails. If the trusted root itself is incorrect, for example, if someone provided you with a fake root, then you might accept invalid data. This is why the root needs to come from a trusted source. In blockchain, the roots are protected by proof of work and consensus. In other systems, they might be digitally signed. The point is, you need to trust the root, but once you do, the verification is cryptographically secure. Verifying multiple items. Sometimes you need to verify multiple transactions from the same tree. Merkle proofs can be even more efficient in this case. If you're verifying transaction C and transaction D, notice they're partners at the leaf level. They share the same path up most of the tree. Instead of sending two complete proofs, you can combine them. You need hash C, hash D, and hash A B. That's 3 hashes instead of 4. The more transactions you verify from the same tree, the more efficient batching becomes. The helper hashes are shared across multiple proofs. This is useful when downloading a block of transactions. You can verify them all together, making it more efficient than checking them one by one. Beyond blockchain. Merkle tree verification isn't just for blockchain. It's used in many distributed systems. Git, the version control system that developers use, relies on Merkle trees. When you clone a repository, Git can efficiently verify you got the right files. BitTorrent uses Merkle trees to verify file chunks. When you download pieces of a file from different people, you can verify each piece is correct. Cloud storage systems use Merkle trees to prove your files have not been tampered with. You can verify integrity without downloading everything. The common thread is, whenever you need to verify data in a distributed system where you cannot trust everyone, Merkle tree verification provides an efficient solution. Key takeaways. Let's summarize the key points about Merkle tree verification. First, verification works by computing a path from your data up to the root using helper hashes. If your computed root matches the trusted root, the data is verified. Second, this is incredibly efficient. The proof size grows logarithmically. Doubling the data size only adds one more hash to the proof. Third, it is cryptographically secure. The properties of hash functions make it virtually impossible to forge a valid proof for invalid data. Fourth, it requires a trusted root. The security depends on trusting where the root hash comes from. In blockchain, that's consensus. In other systems, it might be signatures. Fifth, this efficiency enables practical applications like mobile cryptocurrency wallets, distributed file systems, and version control that would not be feasible otherwise. Practical tips. If you're implementing Merkle tree verification, here are some practical tips to remember. Always verify the order of hashes when combining them. Left and right matter, and getting them backwards will break verification. Make sure you are hashing the actual data bytes, not string representations. ABC as bytes is different from ABC as a hex string. Handle edge cases properly. What if there's only one transaction? What if there's an odd number? Most implementations duplicate the last item to make pairs. Test with known examples. Many blockchain implementations publish test vectors, for example, data with known correct proofs. Verify your code produces the same results. Remember that verification is fast, but creating proofs requires having the full tree. Make sure your system design accounts for who has what data. Conclusion. We've learned how Merkle tree verification works from the ground up using simple explanations and examples. The core concept is elegant. Organize data in a tree of hashes, and verify any piece by computing a path to the root using a small proof. This simple idea enables massive efficiency gains. Billions of data items can be verified with just dozens of hashes. The security comes from hash functions, making it impossible to fake the proofs. The efficiency comes from the tree structure, requiring only logarithmic proof sizes. This is why Merkle trees are fundamental to blockchain, distributed systems, and any application where you need to verify data across untrusted networks. Now you understand how it works. No complex math needed. Just the simple process of hashing, combining, and comparing that makes Merkle tree verification so powerful. Thank you for your attendance. Please consider subscribing to the channel.